Hey, what's going on, guys? Let's do this problem right here. This question is asking, consider 5 meter high and 8 meter long and 0.22 meter thick wall whose representative cross section is given in the figure. The thermal conductivities of various material used, and they have given all the thermal conductivity for each materials. The left and right surfaces of the wall are maintained at uniform temperature, so it means there's no convection, right? If it's uniform, we are starting from this area, so this is going to be starting from conduction. So from here to here is going to be conduction. And then they are saying the temperatures are given. At this one is 300 degree, here it's 100 degrees Celsius respectively. Assuming heat transfer through the wall to be one dimensional, determine A part is asking the rate of heat transfer through the wall. Now let's do the A part first. So let's see how we can find the heat transfer rate. So to do that, let's draw the resistance diagram separately. So here we are going to have a resistance. So that's going to be 1. And if you notice, we have 3 parallel resistance right here. So this is going to be 3 parallel resistance, and then again 2 parallel resistance, and then if you go, the last one is series, right? Series. So let's name everything. So let's say this is R1, R2, R3, R4, and this R5, R6, R7. So this is all we have. Now let's calculate everything individually. So all of them are going to be conduction. So we have to use conduction equation. R1 is going to be equal to, conduction equation is going to be L over Ka, right? So L is thickness. So the first one, thickness is 1 centimeter. That is same as 0.01 meter divided by thermal conductivity. So this is A. A is given by 2. So that's going to be, so this is going to be 2. And the area here we are going to use this height, this 12 centimeter height, and let's say 12 centimeter, and we take 1 meter depth. So this is same as 0.12 meter times 1 meter, and that's going to be equal to 0.12 meters square. So this is going to be the area, right? We know the total area is going to be 5 meter times 8 meter long, but if you assume this height, then you have to separate this one respectively. Like if it's 4 centimeter, you have to divide this one by 3 parts. That's a very difficult thing, right? So what we do, we calculate for this area, then finally we divide this by this area by this one. That's going to give us the total area and heat transfer correctly. So let's do for this area for now and see what we get, right? So here we are going to have K, that is 2, times the area is 0.12, and if you calculate this one, that's going to give you 0.04 degrees Celsius per watts. This is R1. Now R2, let's go and do R2. But if you notice, R2 and R4, so we assume this one R2 and this one R4, right? The bottom part is R4. Okay. We need this one. Okay, bottom part is R4. This is R4, right? And R2 and R4, if you notice, both of them are given by C, and height is same, same material. So it's going to be, the value is going to be same, because the equation we are going to use, R2 is equal to R4, the equation we are going to use, L over Ka. L is thickness is same for both, and K is same for both, and area also same for both of them are 4 centimeter height, so we are going to use that area. So here, instead of 12 centimeter height, we use 0.04 times 1 meter. That's going to give us 0.04 meter square. So this is the area we are going to use for these two. And then B is different. For B, the conductivity value is different, 8, so we can't just equate that one. For these two, both of them are equal. Let's go ahead and plug the values. L is thickness, that is 5 centimeter. Therefore, this is going to be 0.05 divided by conductivity K. So R2 is this one, C. For C, conductivity is 20. So that's the one we are going to use. 20 times the area is 0.04. 0.04, and if you calculate this one, that's going to give you 0.06 degrees Celsius per watts. Now we have calculated R2 and R4. Let's go ahead and find R3. Right? R3 is equal to, again, L over Ka. The thickness is same, 0.05 over K value. K value for B is given by 8. So this is going to be 8 times the area. It's again 4 centimeter height. So we are going to use this one, 0.04 meter square. So this is going to be multiplied by 0.04. And if you calculate this one, this is going to give you 0.16 degrees Celsius per watts. Now we have calculated R4. Now let's go move to the next one. Here we have R5 and R6, right? R5, let's calculate R5. R5 is going to be, so this is 5, and that is 6 centimeter long. So again here area is going to be different. So let's put the equation first. L over Ka. L is the thickness, that is 0.1 over K for D. K for D is 15 times the area. Area is going to be the height times the thickness. Thickness we always keep it 1, and thickness, not thickness, is depth. Depth is always 1, and only the height is going to be matter. So here we have 6 centimeter height, so this is going to be 0.06 times 1 meter. That's going to give us 0.06 meters square. So that's going to be the area for R5. So we are going to have 0.06, and if you calculate this one, that's going to give you 0.11 degrees Celsius per watts. Now let's move to the R6. R6 is same equation, L over Ka. Thickness is again 10 centimeters, so this is going to be 0.1 divided by conductivity. Conductivity for E is given by 35, right? So this is going to be 35, and the area is going to be again 0.06. And if you divide this one by 0.06, that's going to give you 0.05 degrees Celsius per watts. Now we have calculated R6. Let's go to the R7. R7, again same equation, L over Ka. Thickness, L is thickness, that is 6 centimeter. So this is going to be 0.06 meter, right? Meter divided by, let's avoid the units for now. So this is meter divided by Ka. So K for F value is given by 2, right? It's given by 2. So this is going to be 2 multiplied by the area. Area is going to be, this one is full height, right? So we are going to use this one, 12. 12 is the total height, 4 to 4. So this is going to be 12. So this is 0.12 multiplied by 0.12. And if you find this one, that's going to give you 0.25 degrees Celsius per watts. Now we have calculated all the R values. Now what we have to do is, we have to combine the parallel resistance, right? Because we can't directly add them when they are in parallel. So if we combine this one and to make this one to series, then we can directly add them. So let's combine this R2, R3, R4. So when we have resistance in parallel, we add them like 1 over, so equivalent, let's say equivalent resistance is this one, 1 over R2, 3, 4. so this is equivalent resistance. So we are going to add them like 1 over R2 plus 1 over R3 plus 1 over R4, right? So let's plug all the values. So R2 is, we found out right here, that is this one, 0.06. So 1 over 0.06 plus 1 over R3, that's going to be 1 over 0.16, 0.16 plus R4, that is same as R2, that is 0.06. So 1 over 0.06, and if you add them together and find the R1, R2, 3, 4, that gives you 0.025 degrees Celsius. Now this is this combination, this three combination. Now again we have another parallel series right here. So we have to add them like this. Let's go ahead and combine them. So here we are going to have 1 over R5, 6. So let's round this one in case we don't forget, right? So this is degrees Celsius per watts. So R3, R2, R3, 4 we calculated. Now we are going for R5, R6. That's going to be at like 1 over R5 plus 1 over R6, and we calculated the value already. R5 is 0.11, so this is going to be 1 over 0.11 plus R6 is 0.05, so this is going to be 1 over 0.05, and if you add them and calculate this value, that's going to give you 0.034 degrees Celsius per watts. Now we have all this information. Now we have calculated this part, combined this part and this part. Now all of them are in series. Now if I add these two and this R1 and R7, that's going to be the total resistance. Let's go ahead and add them. So let's continue this one right here. R total is going to be R1. So let's write the generic equation first. R1 plus, let's say this is R mid 1. R mid 1 plus R mid 2 plus R7. Now R1 we calculated 0.04 plus the combination is of this one is going to be 0.025 plus R mid 2 we calculated, that's 0.034, and R7 we calculated that one right here, that is 0.25, and if you add them together, that's going to give you 0.349 degrees Celsius per watts, right? Now we have the total resistance. Now we can go ahead and plug it in this this equation. Heat transfer rate, that is Q dot is equal to T infinity 1. So here we don't have surrounding temperature, so we don't have to write T infinity 1. We can write this one like T1 minus T2. So this is going to be T1 minus T2 over R total, right? T1 is 300 and T2 is 100 over R total. We calculated right here 0.349 degrees Celsius per watts, and this is degrees Celsius, and if you calculate this value, that comes out to be 572 watts, right? So 572 watts, but here we have to be careful. We have calculated only for this area, 12 centimeter, but the total area is given by this expression, 5 meter high, 8 meter long. So we have to calculate for heat transfer for that area. So let's erase this part and continue right here. See here, all we have to do is to find the total R total. Let's put the equation right here. Not R total, Q dot total, heat transfer rate total is going to be the Q dot we calculated. Q dot times the total area, that is 5 times 8 times the area we used, that is 12 centimeter, that is 0.12 meter square. So we have to divide this one by this 0.12 meter square, and if you calculate this value q dot, we know that, let's plug that value, 572, we calculated that one right here, 572 times 40, right, 40 divided by 0.12, and that's going to give us the total heat transfer rate. And if you calculate this one, that's going to give you 1.91 times 10 to the power of 5 watts. So this is going to be the total heat transfer rate. And let's look at the B problem. B, the temperature at the point where the section BDE meet. So BDE is this block right here. This meets right here, right? So the point, so here they are asking for the temperature at this point. So here we are going to have two resistance, this resistance and this resistance. This R1 and R mid one, right? So let's go ahead and calculate that one. So let's go ahead and do it. Now we are doing B part. Right, so let's go ahead and write B part is this one. So we are trying to find temperature right here. So let's create the equation. Q dot is going to be equal everywhere. Like in a series, if you combine them in series, Q dot is equal everywhere. Q dot here is equal to Q dot here. Here Q dot. So we can equate this one. So here we are going to have Q dot is equal to T minus T1, right? T minus T, so it comes like T minus T1 minus T, T1 minus T, initial minus final, right? If we put the other way around, we had to put a negative sign in front. So initial minus final, we don't have to put a negative sign in front. So that way it becomes easier. And in the bottom we are going to have these two. So this is the point we are trying to find, right? This is the line. So we are going to have these two resistance. The first one is R1. The second one is going to be R mid 1. This is going to be the combination of all three. So R1 plus R mid 1, right? And let's we are trying to find T right here. So let's rearrange this equation. T, okay, Q, if you rearrange this one, this is going to be like this. T is equal to T1 minus Q dot times R total, right? And if you calculate this one, this is going to be 300. T1 is 300 minus 572 watts times 0.065 degrees Celsius per watts, and that's going to give you 263 degrees Celsius. So this is the answer for the second question. Let's go ahead and do the third question. Third question is asking, if the temperature drop across section F, the temperature drop across the section F. So we have to find the temperature at this location. So let's see how we can find it. So here we only use this part. Let's trace this and continue this right here. So here we are trying to find D part, right? C part. C part, temperature drop at this F. So let's create the equation first. Q dot is equal to delta T over RF, right? Delta T is what we are trying to find. So delta T is equal to Q dot RF. Q dot is 572 times RF. So the resistance at this point is 0.25. This is the one. So 0.25, and if you calculate this temperature difference, that's going to give you 143 degrees Celsius. So this is going to be the temperature drop at this point. And that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.